Now let's see the difference between quartz and quartz glass. Quartz and quartz glass. Navin, welcome to the chemistry class. This was the second time you appear on the screen. I saw you only in the beginning class, inaugural class. And after that, you have completed one chapter, and only after that you are seeing now. Okay. That is left to you. That is also recorded. Now, let us see the difference between quartz and a quartz glass. So you write quartz and a quartz glass. Quartz glass. The difference between these two. Quartz, Q-U-A-R-T-Z. Q-U-A-R-T-Z, quartz. Then quartz glass, Q-U-A-R-T-Z, quartz glass. The quartz and the quartz glass, both are the different forms of silica. These two are the different forms of silica. So the question arises, what is silica? You know what silica is? Silicon dioxide. Silicon dioxide. Now you fuse silica, silicon dioxide, sand, manal, it is fused. You know, sand or silica is SiO2, silicon dioxide. When fused silica is suddenly cooled, it suddenly solidifies, and what we get is quartz glass. It is amorphous. On the other hand, if molten silica is slowly cooled, there is crystallization, and a quartz crystal will be formed. Quartz crystal. So quartz is in the crystalline form. Quartz is crystal, while quartz glass is amorphous. It's not a crystalline. I shall repeat the difference. We are starting with the silica, silicon dioxide, SiO2. It is melted. Then molten silica, silicon dioxide, is suddenly cooled, sudden solidification with the formation of a quartz glass. It is amorphous. If molten silica is slowly cooled, there is crystallization with the formation of a quartz crystal. That's the difference. So we can write the heading you are written. Now let us see the differences. You write. We can write silica, silica, S-I-L-I-C-A, silica. Silica is SiO2, silicon dioxide. Silica is SiO2, silicon dioxide. That is our sand, or even Vellarangal. That is silica, quartz. So silica is silicon dioxide, sand is silica, SiO2. Okay, first up. When molten silica, you write, molten silica, when molten silica is suddenly cooled, suddenly cooled, comma, amorphous, amorphous, amorphous quartz glass is formed. Quartz, quartz glass is formed. Quartz glass is formed. Question. So the question is, what happens when molten silica is suddenly cooled? One more question. What happens? There is formation of a quartz glass that is an amorphous variety of silica. Question. If, if molten silica, molten silica is slowly cooled, so slowly cooled, comma, quartz crystal, quartz, quartz crystal, quartz crystal is formed. There is crystallization, crystallization. So the question is, what happens when molten silica is suddenly cooled? What happens when molten silica is slowly cooled? Suddenly cooled, sudden solidification, and we get amorphous quartz glass. While if it is slowly cooled, slow crystallization with the formation of a quartz crystal. Remember, both quartz crystal and quartz glass, both are different forms of silica, SiO2, SiO2 silica. Okay. Then the next point is about glass. So let us see two properties of glass. Properties of glass. So you write the heading. Simply write the heading glass. Simply write glass. We are going to see two properties of glass. Glasses are there of different forms. There is soft glass, flint glass, Pyrex glass, different forms of glasses are there. Sodium, calcium, silicate, different forms are there. We need study only two properties of glass. Properties of glass. You know, glass is an amorphous substance. Since it is amorphous, glass is amorphous. Since glass is amorphous, it has flow property. You know, in the beginning, we have written amorphous solids are also known as supercooled liquids. Supercooled liquids. A supercooled liquids have the flow property. So you come to glass, it seems to be solid, okay. The glass panes, window, glass panes. See the glass sheets, okay. It seems to be solid, not simply seems to be, it is solid, no doubt. But although it is solid, it is an amorphous solid. It is a supercooled liquid, and therefore glass has flow property. Glass has flow property. Due to the flow property of glass, what happens to the glass panes, glass sheets of windows of very old buildings, Bhargavi Nilayams? You just examine the thickness of the bottom, the bottom and the top of the glass panes of a very old, very ancient glass panes. Pane, pane, glass panes, glass sheets. You can see that the bottom of the glass panes, it will be thicker. It is thicker than the top. Don't think that if you are inserting a glass pane today and if you are going to measure the thickness tomorrow, you will not get the difference. You will not feel the difference. I am talking about the pretty old, ancient, very old buildings, very old buildings. You know, talking about the very old buildings. So the glass panes of or the window panes of old buildings will be thicker at the bottom than the top. The reason is this: glass is a super cooled liquid. It has the flow property, very slow flow property, very slow flow property. And due to the flow property, glass will be flowing down slowly, and the bottom will be thicker than the top. The question will be like this: the glass panes of ancient buildings are thicker at the bottom. Why? So what is our answer, Gayatri? What will be our answer? Louder? I cannot hear you. Ah, a bit louder.
I didn't get the question.
Ah. Okay. Glass, glass is amorphous. It is a super cooled liquid. It has the flow property. Due to the flow property of glass, the bottom of the glass panes will be thicker than the top. Okay, that is one thing. Second, say your glass is transparent. You take out ordinary glass, soft glass panes, it is transparent. But if we examine very old pieces of glass objects, very old glass objects, it is not fully transparent. You can see that there will be white patches here and there. Here and there will be white patches. There is cloudiness here and there. And the cloudiness that is due to the local crystallization. Partial crystallization at that point. See, where there is cloudiness, where there is the white color, cloudiness, at that point, there is crystallization. There is a crystallization. If crystals are there, what happens? When light falls on crystals, light will be scattered. Light is scattered. So due to the scattering of light by the crystals formed at certain regions, there is cloudiness, milkiness, or white patches will be formed. It is not because that the glass object is broken inside. That's not the reason. The reason is this: at that point, at that region, there is local crystallization. If there is crystallization, there will be scattering of light by the crystals formed at that locality, and therefore there will be cloudiness. So we have to remove 2 points, two properties of glass. One is Emmanuel, the bottom of a glass plate will be thicker than the top. That is one property. What the reason, Emmanuel? Bottom of the glass sheet is thicker. Emmanuel, I am calling you. You are looking at the, you are not turning back. I am calling you. Cannot hear me. Evelyn, what do you say? Bottom is thicker. Why?
Because of flow property.
Flow property of glass. It is thicker at the bottom. That's right. Then, very old glass objects, articles, seem to be cloudy, milky here and there. And what reason, Manuel? The white patches, the cloudiness. What the reason? The reason is Gayatri can help Emmanuel.
Because of crystallization.
That is due to the local crystallization. There is crystallization. There is a crystallization. Okay, maybe. It's all right. Okay, so 2 points we have to remember. You please take down, note down these 2 points. You have written the heading glass. Now you write. Glass is an amorphous solid. Amorphous solid. Glass is an amorphous solid or supercooled liquid. Supercooled liquid. Supercooled liquid, comma, with a flow property. Flow property. With a flow property. Glass is an amorphous solid or supercooled liquid with flow property. Supercooled liquid with a flow property. Full stop. So the bottom of window glass panes. Window glass panes. P-A-N-E. Window glass panes. Bottom of window glass panes of ancient buildings. Ancient buildings are written bottom. So you can, it is bottom is thicker than the top. So we can expect a question from this side. Why is it? It is thicker at the bottom. It is thicker at the bottom because of the flow property of glass. Written. Now let us see the second property. Second property you write. Second property. Milkiness, cloudiness or milkiness. Milkiness of ancient glass objects. Ancient old glass objects. Milkiness of ancient glass objects is due to the partial crystallization. It is due to partial crystallization. Partial crystallization. Due to partial crystallization. Due to partial crystallization. What? Written. So 2 properties of glass. One is the flow property. Second is partial crystallization of ancient or old glass objects. Okay, all right. So we can expect 2 questions from here. There. Now let us see the properties of or uses of some of the amorphous solids. Uses of amorphous solids. Amorphous uses of amorphous solids. Let us see some of the amorphous solids. Some examples for amorphous solids. We know solids like plastics, polymers, then rubber, glass, etc. All these are examples for amorphous solids. And we know all these are in, say, frequent use in our daily life. So we can write glass, rubber, plastics, any form of plastic, say polythene, PVC, polyvinyl chloride, etc. Polypropylene, we can study that in the chapter polymers. I think that the polymers will be there. For the time being, it is deleted. But it is a completely application side. We can expect this here. Okay. Glass, rubber, plastics, etc. are amorphous solids. Amorphous solids are amorphous solids used in our daily life. In our daily life. You know, various uses of glass, rubber, plastics, different forms of plastics. All these are amorphous and these are of much use in our daily life. Let us think of a semiconductor. Say, for example, silicon. You take amorphous silicon. Amorphous silicon is a non-metal. That is a semi-metal actually, semiconductor. And it is used in the photovoltaic cells or solar cells. You know, in the photovoltaic cells, in the solar cells, say solar energy, the energy of sunlight is converted into electrical energy. You know, I am talking about the solar panels and the solar cells. Do you remember the solar panels used for the production of electricity? In the solar panels, what happens? What happens in the solar panels? You know, in the solar panels, solar energy, that means energy of sunlight, is converted into electrical energy. Or simply we can say, in the solar cells or in the solar panels, you know, the solar calculator. Nowadays you are not using the calculator. I agree with you because you are having what? Mobile phone with you. So there is no use of any additional calculator. But there was a time when we are using calculator. Then we used calculators, two types of calculators. One is in which say the cells are used, battery is used, calculator. Then another one, solar calculator. Solar calculator is kept exposed to sunlight, that's all. When it is opened, it automatically works. And the sunlight is converted into electricity. That happens there. Okay. If we get a chance, we can study about the working of the solar cells. For the time being, that topic is deleted because that's of much use. That is why CBSE is not interested in that portion. That is deleted now. There is a complete application of our physics and chemistry. But for CBSE, that is not important. CBSE is much bothered about what is the charge of the electron, what is the velocity of electron, what is the mass of the electron. So it is very much concerned about the properties of such things. Not to the application side, not the application side. So it is deleted. But I think that for you it will be again added. Let us hope for the best. Okay. So I was talking about the solar panel, solar calculator. So similarly, say in the buildings we can see there will be solar panels. In the solar panels, there will be a number of solar cells, a number of solar cells joined together. You know, in a solar cell, energy produced is only very small. Electricity is produced is very small. So, if a number of such solar cells are connected in series, a large amount of electricity can be produced. And that is our solar panel. Solar panel. We have seen that solar panel on the top of the buildings. You think of the Cochin airport here. Sial, Cochin airport. You know, the airport is completely working with the help of a solar panel. They are producing their own electricity there itself. And it was the vision of Mr. Kurian, IAS. Mr. Kurian, IAS. He was the founder of that, say, airport. Have you ever seen? You might have seen that airport, but have you seen the solar panels? See? Have you seen? Full of solar panels. So they are using electricity produced with solar panels. Not only that, they are doing something else also. You know what it is? They are selling electricity to KSCB, Kerala State Electricity Board. They are selling electricity. We can also say establish such a solar panels in our home also. We'll get the help from the government side. So we can install such solar panels, and we'll get a help aid from government. We can use electricity for our own purpose, and if excess electricity is there, that will be bought. That will be bought by KSCB. There is every provision for that. Okay? So that what will be the end result? You know, if you are using solar panels, we can minimize pollution. Pollution can be minimized. We need not depend for the hydroelectric projects. We need not wait for rain. You know, in the hydroelectric project, for example, Idiki, Muramatam, or Pallivasan, whatever it is, wherever it is, their electricity is produced with the help of say water power, hydroelectric project. More details you can study it yourself. Okay, so we have to wait for rain. If there is water, if there is rain, there will be water. If there is water, that can be stored in the reservoir. If there is water in the reservoir, that can be channelized into the turbines. And the turbines can be rotated so that dynamo will be working, producing electric current. See? So we have to depend on the mercy of the nature. The nature. I don't say that you should fully neglect nature. You should be with nature, no doubt. Should be always should be with the nature. Okay, hand in hand, no doubt. But you should not always wait for the mercy of the nature's reign. No, we can say insert. We can have a number of solar panels. So instead of thinking, I'm twisting a little from our chemistry. So nowadays, everybody, not everybody, the so-called ruling friend. Ruling friend means The government. Only the government is willing to establish a hydroelectric project at where? Adirapalli. Adirapalli. They are fighting for that. Not we. We are not interested. Nobody is interested. Instead of that, we can have a number of solar panels. Why can't we spend that money for establishing the solar panels? Okay, let me come back to chemistry. Otherwise, you will scold me at the end. Okay, I'm not a politician. I'm not against any government. Just criticizing. I'm not a cynic, but I'm a critic. I'm not a cynic, but I'm a critic. Nevin, I'm not a, I'm not a cynic, but I'm a critic. I'm a critic. I will always say out the plus and the minus points. That's right. Just like our the capacitor with plus and minus charges. Hmm? Plus and minus charges. No, capacitor simply to charge the rods, charge the plates. That's a capacitor. Is it not? Between these two, there is a medium, and that medium is called Achu. What is that medium called? Ma'am was taking the class last period. Sharon, we have two charged plates, and that constitutes a capacitor. Okay, I agree with you. Now, between these two plates, there is a medium. She was talking about the two media, eh? Air and some other medium. No, two medium, you will see. So I'm talking about suppose there is air only. There is a medium between these two. And the medium between these two, that's known as very good. That is called a dielectric. Dielectric. Remember that the medium between two charges. That is the dielectric. If there are two charged plates, plus and minus charged plates, and there is air only, then air is the dielectric. The medium is the dielectric. Okay, dielectric. And for the medium, there is a property known as dielectric constant. No. So easily you are forgetting things. But not the subjects study. You must forget things, not the things like this. What is Gauri? Video is off. Okay. Okay. It's all right. Sometimes it happens automatically. I think that it is time to stop this nonsense. That maybe the video is getting off automatically, naturally. Okay. So what was I talking about? The dielectric constant, the medium and dielectric constant. Okay, let us come back to this, the solar cell. So in the solar cell or solar panel, solar cell or a solar panel is a combination of a number of solar cells. Solar cell is the same as photovoltaic cell, photovoltaic cell in which sunlight is converted into electricity. There we make use of amorphous silicon. Amorphous silicon. Amorphous. We are talking about uses of amorphous substances. So amorphous silicon, slices, small pieces of a silicon that is used in the solar cells. So we can write that. You continue our say discussion. So glass, rubber, plastics, etc. are amorphous solids used in our daily life. Next para you write. Next para. Next para. Amorphous silicon. Amorphous silicon. You write. Amorphous. Amorphous silicon. Amorphous silicon is used. Amorphous silicon is used in photovoltaic cells. Photo means light. Photo means light. Photo photovoltaic, voltaic, photovoltaic cells or solar cells, solar cells, solar cells, solar cells. And what is happening in the solar cells? Come. In which, in which, in which sunlight, energy of the sunlight is converted. Sunlight is converted into electricity. Electricity. You think of Sian, Cochin International Airport Limited. So, photovoltaic cells or solar cells in which sunlight is converted into electricity. Energy of a sun rays is converted to electrical energy. And such devices are photovoltaic cells or solar cells. Okay, application of a silicon. All right, you followed this or not? Achu, what do you say?
Yes, sir.
Okay, simply saying yes sir always. I don't know whether you follow this or not. If you follow this, you immediately say yes sir. But you are late to say answer. Okay. Now let us see the classifications of crystals. Classification, you're right. Classification of crystalline solids. Crystalline solids. Classification of crystalline solids. Classification of crystalline solids. Here we are going to classify the crystals based on the constituent particles. We know in crystals there will be the constituent particles. The constituent particles may be atoms, may be ions, ions of the same type or opposite types, plus minus, ions, or there may be molecules even. The particles may be atoms, ions, or molecules. And we can call them in general as particles, constituent particles. So based on the nature of the constituent particles, we can classify crystalline solids into 4 types. There are 4 types of crystalline solids. Let us see one by one. Write the heading. Write the heading. Classification of crystalline solids. Okay. One. Number 1. Molecular solids. Molecular solids. Type 1. Class 1. Molecular solids. You can easily say what is the composition of molecular solids. You know, in the molecular solids, the constituent particles will be, just guess. You guess it? Molecular solids. Just guess it. Right or wrong doesn't matter. Actually, you try. You know, right? Molecular solids. Composed of the constituent particles will be molecules. The constituent particles will be molecules. So they are composed of molecules. You know, in the crystals, there will be certain points at which the particles are arranged. Say, points like this. You need not draw this. I shall ask you when it is needed. See, there will be certain points. Na plus Cl minus, Na plus Cl minus, etc. So there will be certain points at which the particles are arranged. And at these points, there will be molecules. So, molecular solids are composed of molecules. Molecules may be polar molecules. There may be non-polar molecules. There may be polar molecules or non-polar molecules. Non-polar molecules means in the molecule there is no charge separation. There is no charge separation. H2, O2, N2, or the noble gases like He, helium, Ne, neon, argon, Ar, etc. For the noble gases, molecules and atoms are the same. They are monatomic, monatomic. Monatomic means there is only one atom in the molecule. One atom in the molecule. So, you take a, say, for example, argon, noble gas. Its molecule and atom, both are the same. Both are the same. But you take hydrogen, H2, it is diatomic. 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 Just listen only. This is a monatomic. Monoatomic or a monatomic. Monoatomic or monatomic. There is only one atom in the molecule. That means the molecule and the atom both are the same. H2 diatomic. There are two atoms in the molecule. O2, N2, etc. All these are diatomic. When I go three, diatomic. There are three atoms, triatomic. And all these, you just forget about O3, slightly different. You take the others, say argon, hydrogen, oxygen, nitrogen, etc. And you study the, we know these are gases, no doubt. These are gases. Now you cool down, you lower the temperature, and ultimately there will be formation of the liquid, and the liquid is converted into the solid. There will be crystallization at a very low temperature, minus temperature. So all these crystals will be composed of non-polar molecules. Non-polar molecules. All these are, please don't write, all these are non-polar molecules. If there are non-polar molecules, the molecules are held together by means of the cohesive forces, the intermolecular force known as the London forces. Do you remember? Last year we have studied the dispersion force or the London force, dispersion force or a London force. Forgotten everything. Very good. So I get a chance to explain that again. Okay, thank you very much for getting on these things. Okay, so what is the dispersion force? What is the London force? London force, you know, due to the oscillation of the electron cloud. Remember now, the electron cloud will be shifted to one side so that there will be temporary transient dipole formation. Eh? Temporary dipole, transient dipole, and there will be attraction between such a temporary dipoles, transient dipoles, and that's called the dispersion force or the London force. London is the name of a scientist, not your London city. This is a name of a scientist, the London force. Okay. But the attraction is very weak. That's only very weak attraction. So what happens? They have very low melting point and very low boiling point. So they are easily converted into the liquid state or the gaseous state. Gaseous state. Very, very low attraction. There is no charge separation. So they are insulators, non-conductors of electricity. They are very smooth also. Let us think of polar molecules. Say, for example, polar molecules like ammonia, or sulfur dioxide, or HCl. We take such molecules. Yes, sir, sulfur dioxide, SO2, ammonia. You take these molecules. And in such molecules, there will be charge separation. What is it due to? Why is there the charge separation? This is a partial plus, partial minus. Why is it so? What the reason? Aju?
Lateral forces.
Uh, charge separation. Charge separation is due to why? Evelyn, you are there. Can you try what the reason for the charge separation? Cannot. Nandana, can you try?
Dipole moment.
Pardon?
Dipole moment.
Dipole moment? Dipole moment is a result of a formation of dipole. And how is the dipole formed? Two poles are formed. Why? How is it formed? Okay. There is a difference in electronegativity values. There is difference in the electronegativity values. So the electron pair will be shifted towards the more electronegative atom. So the more electronegative atom gets partial negative charge. And the less electronegative atom gets partial positive charge. And such molecules are polar molecules. Okay, polar molecules. If a molecule is polar, it will have a dipole moment. That is right. Dipole moment is charge into distance. Charge into distance, that is dipole moment. So there will be a dipole moment. If there is a dipole moment, there is attraction between the dipoles. Attraction between the dipoles. Then it is called a dipole-dipole interaction. Dipole-dipole interaction. That is a still stronger attraction compared to the former one, London forces. Now you come to water, ice. There is strong attraction between the water molecules through a special type of bond known as, what is that bond? The bond between water molecules, the bond between the water molecules, hydrogen bond, hydrogen bond. So there is a strong hydrogen bond between water molecules. Okay. So in the molecular solids, there will be molecules at the definite points. The definite points. The definite points have got a name that we'll see later, not now. Just wait. So they are composed of molecules. The attraction between the molecules may be either the London forces or dispersion forces, or the attraction may be dipole-dipole attraction, interaction, or the attraction may be through hydrogen bonds. Hydrogen bonds. Anyhow, all these compounds, all these solids have low melting points. They are either gases or liquids. If it is a solid, It will be very smooth solids with a very low melting point. Okay, they are insulators of electricity also. So that's about the molecular solids, about the molecular solids. So let us write about the molecular solids. Write about the molecular solids. So you write the heading you are written. You are written the heading molecular solids. Okay, you are right. Molecular solids. Molecular solids are composed of molecules. Composed of molecules. They are composed of molecules. Composed of molecules. First, the molecules are held. The molecules are held. Molecules are held by dispersion forces. Dispersion. In brackets, London. Dispersion or London forces. Or dipole interaction. Dipole interaction. Dipole interaction. Attraction between the dipoles. Dipole interaction. Or hydrogen bond. H bond. Hydrogen bond. I don't know what happens to the video. Hydrogen bond. We can see three types of intermolecular attractive forces. Maybe the dispersion force or London forces. That is in the case of no polar molecules. And between polar molecules, there will be dipole interaction. And if there is a hydrogen bond between the molecules, then the attraction is due to hydrogen bond. Let us see one by one. As a next para, you write. As a next para, you write. Right. Non-polar molecules, non-polar molecule. So I got so like non-polar. Okay. Non-polar molecules are held by non-polar molecules are held by dispersion or London forces. Dispersion or London forces. Dispersion or London forces. Dispersion or London forces. Full stop. So what happens here? There will be very weak attraction. There is no charge separation, and therefore they are non-conductors of electricity. You put a hyphen, then you write non-conductors of electricity. They are non-conductors of electricity. Non-conductors of electricity, they are soft. If solid, soft, and low melting points. They have low melting points, very low melting points. Let us take some examples for this. Examples. Examples. The noble gases like argon, argon, then hydrogen, then chlorine, from iodine, etc. Iodine, etc. They are composed of molecules. There will be, the particles will be molecules, non-polar. Non-polar molecules are held by London forces or dispersion forces. Examples, argon, hydrogen, chlorine, iodine, etc. No, the first three are in the gaseous state, no doubt. Okay. Next para you write. Next para. Polar molecules, next para. Next para. Polar molecules are held by polar molecules, right? Polar molecules are held by polar molecules are held by dipole-dipole interaction. They are dipoles. Dipole, dipole, both are dipoles. Dipole, dipole interaction, attraction. Dipole, dipole interaction. Dipole, dipole attraction. Let us take two examples. Examples. Examples HCl, HCl, SO2, sulfur dioxide. There will be charge separation. Ozone also. So many we can have. So many examples we can give. Then, next para. Next para, you write. Say molecules containing molecules containing fluorine, oxygen or nitrogen may be held by hydrogen bonds, H bond, hydrogen bonds. Hydrogen bonds. There will be hydrogen bond. Example, water. Example, H2O, water. That is in the form of ice. Water. So that's about the molecular crystals. Composed of molecules, very weak attraction between the molecules. So they are smooth, low melting point, and boiling point. They are non-conductors of electricity. In the non-polar molecules, the molecules are held by, come on, non-polar, held by London forces or dispersion forces. Then polar molecules held by dipole-dipole interaction. Molecules containing fluorine, oxygen, nitrogen, etc. may be having hydrogen bonds, for example, in water. The question is this. Oh, the question will be like this. You will be asked. Say, what is the intermolecular force of attraction existing in ice? That's the question. Naveen, the intermolecular force of attraction existing between water molecules in ice? Name the intermolecular force. Did you say anything? I did not hear what you said. Okay, Achu, a bit louder, you say
H2.
Right.
hydrogen bond. Hydrogen bond. Was it the answer given by Nevi? I did not hear you. Okay. So that is the question asked. Nothing else will be asked. Not examples, not examples will be asked. This type of questions will be asked. Okay. Say another question. Say what is the binding force between molecules in HCl? You will be given
Dipole.
multiple choice, dipole interaction. Multiple choice dipole interaction. Such questions will be asked. Not the examples will be asked. Okay. So let me stop now. This time. You can see me. You can see again in the next.